All right, for our last example with rational functions, I've got a function here. It's a second degree polynomial over a second degree polynomial. And we're going to go through the same list of items to try to determine the complete graph of this polynomial or of this rational function. Okay, so we'll start off first by factoring and finding the zeros of both the numerator and denominator. We'll take them one at a time. Let's take the numerator first. I'll set that off to the side here. Now I want to factor this polynomial. Now we haven't done a whole lot of factoring in this course. I assume that a lot of it is review, but I'm going to go through and show you a shortcut to factor a polynomial, a trinomial, with the leading coefficient that is not 1. Okay, we've done a few of them where they are 1. And so in this case, I'm going to call it the modified AC method. The AC method is a little bit longer. It's probably more familiar to you. But this one we're going to call the modified AC method. It's kind of my my little shortcut that I like to use. And so you can use whatever you're most comfortable with, but I'm going to show you this modified AC method, and then we'll use it on the denominator as well, because it also has a leading coefficient that is not 1. Okay, so on here, the modified AC method is this. You take the A times the C. AC is equal to negative 18, right? 6 times negative 3, right? A, B, C, you get your 3 terms. A is leading coefficient, C is a constant. And then you have to find factors of negative 18 that add up to the negative 7. Well, in our case, it'd be 2 and negative 9. Okay, 2 and negative 9. Their product is negative 18. Their sum is the negative 7 in the middle. Okay, so now what we need to do is create our factors using these numbers. Now, if you were doing the AC method, you would start with this, and then you would separate out the middle term into these 2 terms, do some grouping, a little bit of a lengthy process. But here with this modified AC, we're going to go straight to our factored form in a set of parentheses. We're going to use the 6x squared. We're going to split that up, but we're actually going to not split it up correctly. We're going to use 6x and 6x. Now obviously the factors cannot both be 6, because when I multiply them together I would get 36x, 36x squared, not 6x squared. So we're going to have to remove a 6 in the end here, which we'll do in a moment. Then I also have this 2 and the negative 9. I'm going to put those in as my constants in those factors. Okay. Now the way that we remove the 6 is a little bit interesting. We're going to divide out any common factors that that exist within the factors themselves. So if I look at 6x plus 2, there's a common factor of 2 between those 2 terms. And so I'm going to divide out the 2 from each of them. Okay? And what I'll be left with is the factor 3x plus 1. Right, if I divide each of those by 2, the common factor. Now let's repeat that process with the 6x minus 9. So they have a common factor of 3. I'll divide that out. Okay, so divide out the 3, divide out the 3, and what I will have left is a 2x minus 3. Now notice what I ended up doing in the end is I divided out both a 2 and a 3, which together make a 6, which is what we needed to divide out. And so now I have 3x times 2x, that's 6x squared. And if I were to FOIL this or distribute this back out, I would end up with the original 3 terms, right? 6x squared, I'd have minus 9x plus 2x, that gives me the minus 7x, and then a minus 3 on that combination. So if I distribute that back out, it should simplify back to the original polynomial. Let's repeat that for the denominator. Okay, make a little space. And so I have 2x squared minus 7x plus 6. Again, our AC, leading coefficient times constant. AC is going to be 12. Factors of 12 that add up to negative 7. Well, our options are, what, 1 and 12, 2 and 6, 3 and 4. Well, 3 and 4 is the obvious choice. They both have to be negative in order to make a product that's positive and a sum that's negative. Okay, so negative 3 and negative 4 will work. So now what I do is I put those into the factors along with 2x. Okay, so it's going to be 2x minus 3 and 2x minus 4. And again, I have an extra factor of 2, right? 2 times 2 makes 4, not 2, and I multiply to get that first term. So I have to divide out a 2. Well, nicely enough, there's a common factor of 2 in one of these sets of factors. And so I'm going to divide out the common factor of 2 from the 2 and the 4. That's pulling my 2 out. And the remaining factors are 2x minus 3, and we get x minus 2. Right, if I divide that 2 out from each of those terms. And so now I have both factors, both factored forms. Okay, so my original polynomial, or my original rational function, I'm going to go ahead and write it out over here on the side, is going to be, it was 6x squared minus 7x minus 3, all over 2x squared minus 7x plus 6. If I factor it down, I'm going to get 3x plus 1 times 2x minus 3, all over 2x minus 3 and x minus 2. Okay, so that's my factored form for each of those polynomials. I'm going to clear myself a little bit of space here so I can do some other work. Okay, and so now I've factored, and now I got to find the zeros at the top and the bottom. So I'm going to stick with that. Let's take the top. Well, the zeros of the top, I take each of those factors, set them equal to 0, and solve for x. Now, hopefully you guys can do this pretty quickly now. If I subtract the 1, divide by the 3, we're going to get a negative 1/3. Okay, so that's using, if I was doing this as a 2-column problem, which you're going to need to do probably at some point, I would write next to that EQ1 and EQ2, because those are the 2 steps that I use to get to that point. Okay, same thing here. I would add the 3 and divide by the 2. That would give me a 0 of 3/2. Okay, so again, EQ1 and EQ2 are my properties there that I'd be using from our property index. Okay, now I'm not writing all that down, but you guys have enough practice with that probably by now where you could fill that in. Okay, so those are my zeros for the top. Now the zeros for the bottom, that's going to be taking these 2 factors on the bottom, setting them equal to 0. So it's going to be 2x minus 3 equals 0. That's going to be, again, we're going to add the 3, divide by 2. That gives us the 3/2. And then I take my x minus 2, set that equal to 0, and of course you just get 2. Okay, so of course here you'd have EQ1 and EQ2 again. Here you just have the EQ1 because I use the addition property to move that 2 over. Okay, so those are my zeros. Now remember, so that finishes off part 1. Okay, did the factoring, got my zeros. Part 2 is to figure out, use all the zeros and the factors to figure out all this stuff, the domain, vertical asymptote, all that stuff, okay? So let's look at the domain first of all. The domain occurs when you pull out the factors or pull out the zeros from the denominator, okay? So I'll put the domain down here. The domain is going to be all real numbers except 3/2 and 2. Well, 3/2 is 1.5. So I could write that out in interval form, -infinity to 3/2, union with 3/2 to 2, and then union that with 2 to infinity. Okay, so those are my 3 intervals. And of course, if I wanted to write that in set form, which we've done before, it's just x not equal to 3/2 or 2. Okay, so either of those, they're equivalent to each other, of course. Okay, so there's my domain. My vertical asymptotes, remember, well, actually, let's skip that. Let's go to the holes. Because remember, holes occur when your zeros when you have a 0 that's the same number for both the numerator and denominator, which we actually have here, right? The 3/2 occurs in both the numerator and denominator. So there is a whole at 3/2. Okay. Now I mentioned in the past how to find the y-coordinate of that whole. Okay, so a whole is a point that's pulled out of the graph. To find that, what we need to do, and remember, if I plug 3/2 into the original function, I'm going to get a 0 over 0, which is undefined. But if I reduce this function down by canceling out common factors like the 2x minus 3, then I get a new function where that whole is defined. Okay? And so if I plug in 3/2 into my new function, then I get the y-coordinate of that point. All right, so I would get, let's see, 3x plus 1 over x minus 2. And actually by doing that, I've actually completed step 3 to write this into lowest terms. But then I can find the whole, the other part of the whole, by plugging in my 3/2. So I'd get 3 times 3/2 plus 1 over 3/2 minus 2. Okay, well, let's get all these common denominators here. This would be 9/2 plus 2/2, right? 1 is 2/2. And then here's 3/2, and 2 is really 4/2, so that'd be minus 4 over 2. Okay. And then I can combine my numerators. It's going to be 11/2 over negative 1/2. And if I copy dot flip or multiply by the reciprocal, I get 11/2 times negative 2 over 1. The 2's will cancel and I just get a negative 11. That works out actually really nice. Okay, so the whole is actually going to be at the ordered pair 3/2 or 1.5 comma 11. Oh, negative 11, sorry, negative 11. Okay. Okay, so that's all my work to get the ordered pair for the whole. So that's the point that's actually removed from the graph. Okay, vertical asymptotes occur at zeros of the bottom only. That's going to be at 2. So vertical asymptote is going to be x equals 2. And the x-intercepts occur at zeros of the numerator only, which in our case would be a negative 1/3. So there's going to be an x-intercept at negative 1/3 comma 0. Okay. Now the other thing that's interesting is the multiplicities here. Now, everything has a multiplicity of 1, right? All the powers on these factors are 1, so they all have odd multiplicities. And so our vertical asymptote, that means the graph will approach that vertical asymptote in opposite directions, one going up and one going down. So opposite directions. And the x-intercept, because that has an odd multiplicity, we know the graph will cross the x-axis there. Okay, so it's crossing the x-axis or going through, not touching. Okay, so I've got all that. We already completed part 3. That's my simplified fraction, or simplified rational function. Then my y-intercept. Let's look at the y-intercept. That's what we get when we plug in a 0. Well, interestingly, what we get, we could actually plug into the simplified form. It will work out a little bit nicer. I could actually plug it into the original as well. It doesn't matter. You get the same value because every point is the same on the simplified form and the original except at that hole. Okay, the simplified form doesn't have the hole. The original form does have a hole. It has that point pulled out. Okay, so if I look for the y-intercept, I plug in a 0. Well, I get 0 plus 1 over 0 minus 2, right? The x terms become 0. And of course, the y-intercept is the ratio, we'll call it the ratio of the constants, which of course is negative 1/2. And that would be the same if I used the original. It'd be negative 3 over 6, which reduces to negative 1/2 also. So my y-intercept is at 0, negative 0.5 if I want to write that out as a decimal. Okay. Now I need my horizontal or oblique asymptote. And when I look at these, look at the two polynomials, the degrees are different. Or I'm sorry, the degrees are the same. I don't know why I said different. The degrees are the same there. Okay, they're both 2. And so that implies that we're going to have a horizontal asymptote. And the value of the horizontal asymptote will be the ratio of those two numbers, the leading coefficients. So the horizontal asymptote occurs when y equals the ratio of leading coefficients, which in our case is 6/2, which then reduces down to 3. So our horizontal asymptote will be up at 3 units high. Okay? Okay. Now we're going to look at the points of intersection between the horizontal asymptote, because we don't have an oblique, so it's the point of intersection with the horizontal asymptote next. Okay, so then we find that value, or that point, by plugging the 3 into the other side of into the y value in the function, and of course we'll go to the simplified form for this. And so we solve the equation 3 equals 3x plus 1 over x minus 2. Okay, so we're just solving this equation. So we're looking for the x value where the function equals 3. That means the function crosses a height of 3, which is where your horizontal asymptote is. Okay, so to solve this, I would multiply both sides by the denominator of x minus 2. So multiply by x minus 2, multiply this side by x minus 2. Again, I'm getting a little tight on space. So I get 3 times x minus 2. Well, that's 3x minus 6 if I distribute it. And on the right, the x minus 2's cancel, and I get 3x plus 1. Okay, this is kind of interesting. Right here, if I were to subtract the 3x to move the x's over, they'll cancel out on the right, but they also cancel out on the left. And so here I get negative 6 equals 1, which is a false equation. It's an equation where there's no more variables and the two numbers are not actually equal to each other. And so when you get a false equation, that means there's no solution. So this is a false equation, meaning there's no solution. If there's no solution, that means there are no points of intersection with the original horizontal asymptote. Okay, so no points of intersection. So I could say for this one, there's none. All right, and that's because we got this false equation here. Okay. Okay. So I think that pretty much covers all of our bases. We've got all this information. It's very useful. What I'm going to do now is streamline some of this, get a nice list of all this information, and then we'll go ahead and plot the graph based upon that. So I want to erase some of this work. Let me get rid of my factors here and shrink this down so that I have the original and the simplified form only. Just trying to save a little space here. And then I don't need this. I know there's no intersection with the horizontal asymptote. Let's see. I know that if I make a list here, I know the horizontal asymptote is at y equals 3. Just going to try to shrink this down as much as I can. So I have a bunch of space at the end for my graph. The y-intercept is going to be, where'd my y-intercept go? Right here, 0, negative 0.5. That's good. Getting rid of some of the work. All right, I've got my vertical asymptote at x equals 2. And remember, that's where they're going in opposite directions. And then the x-intercept, put that down here. The x-intercept occurs at negative 1/3, 0, and it crosses. gets rid of some of this stuff. We also have a hole. Put the hole in there. The hole is at 1.5 comma negative 11. And the rest of this was just work in finding the zeros, which I now already know and I've used them. So I'm going to erase all that. Normally I would keep that information, but I'm trying to make room for my graph. Okay, so this should be everything I need. Now I can plot my graph. All right. Okay, so as I look at this information, most of this stuff is very small numbers, right? Lots of 0.5s and 1/3, lots of fractions in there. I do have this negative 11 on the whole. That's a y value, so we could go down to that. Yeah, so maybe I'll even extend this vertically down a bit farther just to make sure I have enough space. Okay, so let's go ahead and start marking this off. My horizontal asymptote's up at 3, vertical asymptote's over at 2. All right, so I guess horizontally, let's just start marking this off. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I hit 11. Perfect. Okay. And so now I got to plot this stuff. So horizontal asymptote is up at 3. Okay. I've got a vertical asymptote at 2. I've got a y-intercept at negative 0.5, so there's my y-intercept. I've got this hole at 1.5 comma negative 11, so there's a hole right there. Okay, I've got an x-intercept at negative 1/3. Well, that's really tight in there, right? The x and y-intercepts are very close to each other. That pretty much is everything, okay? So if I were to plot this out, I can tell right away, I know that this graph goes through the x-axis here, and it has to come up through and go approach this horizontal asymptote. So I know it's going to go up and back like so. And then it has to come down to the vertical asymptote, but I have to skip over that hole. Okay. Let's make that a little bit smoother. Oh, I'm missing. That is not going well. There we go. Okay, something like that. So I've got this little hole in the graph, just a little pinprick pulled out, okay? The way we represent that is just by putting an open circle there, but technically you wouldn't even really be able to see it. It's such a small spot. And then I know also that at the vertical asymptote, where is it? Vertical asymptote, the graph approaches that in opposite directions due to the multiplicity. So if it's going down to the vertical asymptote here, it must be coming from above on the other side, okay? Otherwise, if that was an even multiplicity, they'd be both coming down. So this is odd, so one side goes up, and so I can sketch that part of the graph in up there, okay? All right, and so that gives me a pretty complete graph. That's all the details that I need, and of course, we could verify it once on the graphing calculator just to make sure. So I'm going to go ahead and plot the original function just to make sure I didn't make any mistakes along the way. Again, putting the numerator in parentheses. Okay, so I've got it started. You can't really see all the details there, but the rest of the denominator runs off the screen, but they're there. Okay, then I'm going to hit window, and I'm going to adjust my window to pretty much look like this graph here. Okay, so I'm going to go in the x direction. I think this was 8. 1, 2, 3, 4, 5, 6, 7, 8. So -8 to 8. I think it was 1, 2, 3, 4, 7, 8. Yep. And then we went -11 up to 3, 4, 5, 6, 7. Okay, so I've got that window. And I hit enter. Actually, no, I hit graph. Okay, and you can see that looks pretty good. Okay, it's pretty much exactly what I have, just, you know, calculator doesn't look as good as mine, right? I've got the asymptotes in there, some of the detail, but it looks to be the same thing, okay? So I would say we did not make any mistakes. Now, the weird thing is the calculator does not show the hole, right? There is a hole, but the calculator, because that point is so small, the calculator actually can't display it on here. There are ways to make it work, but you have to kind of line the hole up to the center of the pixel, and it's very hard to do. We're not going to worry about it. But to prove to you that that hole exists, if I went to my calculate menu, if I hit second and then the trace button, and I type in value, most values I plug in an X and I'll get a point out. But if I were to plug in 1.5 and hit enter, there's no Y value, right? Gives me no result because there's a hole there. Okay? Now what's interesting is if I do the same thing, if I were to remove that original function and put in the simplified form, so I put in 3x plus 1 divided by x minus 2. Okay, so I got that function in, and then hit graph. What you'll see is exactly the same graph because the two are the same, right? These two functions are exactly the same with one exception. The simplified form will have that hole filled in. Kind of interesting. And so if I go to second, calculate, hit value, and now if I type in my 1.5, I get 11. Okay? So on the simplified form, the hole is filled in. On the original form, the hole is not filled in. Okay, so we have the hole there. And what we're ultimately trying to graph is the original function. The simplified form is nice. It's useful for finding some of this other information, but it's missing, you know, it doesn't have that hole. So we want to make sure to plot the original function, which includes the hole, rather than the simplified form, which would fill in the hole. Okay? And so that really gives us all the details that we're looking for, and I hope that helps you as you go through your examples. Now there's a variety of different types of examples. We've now seen one with an oblique asymptote, a horizontal asymptote at 0, and now a horizontal asymptote that's not at 0. So we've seen a lot of the different possibilities, but of course you can combine these things in a lot of different ways and get some very complicated graphs. But they all have these same general features to them, and you can find them now hopefully using these techniques.